welcome back again to educator.com. We have another lesson in intermediate C++. Today we are talking about containers, and specifically list containers, linked lists. All right. Now we're going to talk about a few things, including a brief comparison of a linked list and vectors. We had vectors last time, we have linked lists this time. So we're going to overview how linked lists work. We compare them a little bit to how vectors work. We access the list elements via a method and via iterator. We've talked about iterators before. We're going to compare the vector iterators to list iterators. They're subtly different. Get the information about a list, modify the list elements or the list itself. We'll modify the list. We'll have some examples. We'll merge, splice, sort, and reverse a list. A list is, like a vector, is a sequence container. So the sequence is important. And we'll provide some functions for custom sorting. You may not like the way the system sorts things. The system may not be able to sort your object without you giving it a custom sort routine. And a few other containers that use the linked list, container adapters, specifically the deck. It looks like DQ, but it's pronounced deck, stack, and queue. All right, a little quick overview here. Now, we've seen arrays, we've seen vectors. The data is kept in contiguous memory. Now, here's a nice little picture. We've got some numbers. I'm not going to read these numbers off for you. Insertion and deletion can be expensive. You see, we have a 271 we want to put in there. We want to put it in this particular location because we want to keep it in order. Now, what that means is we got to move that to there, that to there, that to there, blah, 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 until we get to the end. Now, if this is going on for hundreds or thousands of elements, you see this may take a little bit of time. Erasure, removing, deletion, the same problem. So we want to, like, erase this one. Well, guess what? We have to move all the other ones over all the way. And there's hundreds and thousands of them. That can take a little while. It can take a long time, not only in computers. You say, oh, computers are fast, they take microseconds. Well, no, sometimes it can take a visibly length of time. You're sitting there waiting for it to do something. A human perspective, long time, depending on what you're looking at. I mean, these looking at all these are integers. What's the big deal? Those could represent, instead of integers, they could be a large, complicated object that you've designed. And you have an array of those objects. And if you have to physically move all of these objects, it could be time-consuming. So if you need to do a lot of insertion and deletions, an array or a vector may not be the container you want. Now, your linked list container solves that problem because the data is stored in these nodes, and the nodes are scattered all throughout memory. So here we have the 15 is there, the 27 is there, the 82, blah, 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 all the way around here. So now we have a new node we want to add. We don't have to move anything around. All we have to do is take this pointer that's from 267 to 275 and erase that pointer and have it point along this green line to the 271, and then have the 271 point to its next, which is 275. So now we've only moved a couple of pointers around, and now all of a sudden the linked list has got a new node in order where you want it. Here's a brief description of how something like this might look as a structure. We have a struct linked node. Double is the value, which would be like 342 or 271 in this case, etc. And then a pointer to the next node in the linked list. Here's how we define the top pointer, which points to the top of the linked list. From the top, you can go to the next, to the next, to the next. Sometimes it would be called the front. In this particular case, I happen to call it top. And I have a temp pointer, which you can use to, I need to save the previous pointer while I'm moving things along using the temp. We also have new node, which I did not define down here, should have, which happens to be pointing to the node you want to insert. But accessing the nth node, there's trade-offs everywhere you go. If you need to access the nth node, it may not be as cheap as an array. With an array, you've got your pointer to the first spot of the array. I need the 27th node. Well, you take this point, you add 27 to it. I don't know where we are in the list. Let's say it puts it at this position. So this address plus 27 points you right to where you want to go. Linked list, you start here, you start counting. Go to the next one, go to the next one. And each time you go to the next one, you increment your pointer until you get to number 27. Here's our 27th node. So you have your trade-off between being able to insert and delete quickly and being able to access a specific node quickly. So here's how we include it. We want the list definition, and it's similar to other containers. It's similar to the vector. So we have an empty method. Is the list empty? There's things you don't want to attempt on an empty list. How many elements do we have in the list? What's the maximum size that is allowed in this system at this time for this list? It's pretty much the same way as a vector. You've got X bytes of memory in there, divided into however many bytes are in each node, and that's how many you're allowed to put in there. There's no capacity because linked lists are completely dynamic. It's not an issue of have we filled up our capacity? Do we need to allocate more capacity? Every time you add a new node, it needs to allocate new space for that node. Now we can resize it, give it a new size. What that will do, unlike a vector, when you resize a vector, it just gives you some more space to start filling up with nodes. The linked list will actually add new elements, and it'll call the default constructor if you have one. If you don't have one, you'll get an error. So if you have a linked list of integers, well, the default constructor just give you a 0. If you have some other type of object, your object should have a default constructor that you can do this, and it will add them all, and it will link them all together, and you'll have a linked list with a new size. If you shrink it, it will just destroy the ones on the end and call the destructor. So you may not want the default constructor, so you can give it a value. So it would add new items to the list, and they will be initialized to whatever value you give it. And like I said here, if the new size is smaller than the current size, it will destroy elements. Now here's how we access the linked list. We want the front, which is pretty much like the same with the vector. We want to return the actual first element back, give you the last element. Then here's your iterators. So you need to loop through the linked list using iterators. Begin the iterator at the first element and the iterator at the last element. RBegin is the last element for reverse iteration, and RN is the first element for reverse iteration. So you can go from RBegin to RN. When you say iterator plus plus, you're actually going backwards through the list. So here's a quick example. We have a list of type string. It's called mylist. And I happen to have it defined here. We've got it pointing to Frederick, who's pointing to William, who's pointing to Zachary, who's pointing to Bartholomew, and Bartholomew is pointing to null. That's the null indicator, meaning that there's nothing after this one. So if we say print out mylist front, it will print Frederick. Mylist back, it will print, of course, Bartholomew. Very easy, very simple. Now, list iterators are a little different from vector iterators. A vector iterator is almost literally just a pointer to an element into the vector. A list iterator is also a pointer, but there's things you can't do with a list iterator that you can do with a vector iterator. And it's basically because the next element might not be right after it. In a vector, it's contiguous memory. The next element is right after it, right after it, right after it. You literally could have a spot in memory. Let's draw a real quick memory grid here. And this guy's next might actually be above it. So you can't say this pointer, this address plus 7 is the next link. You know, it doesn't work that way. So you don't have a less than or greater than concept, which bugs me personally, but you don't have to worry about that. So vector iterators allow integer add. There is a less than, there's a greater than type of thing. So like here's an example of a vector. So we have a vector of integers called v3, and we'll just load in some arbitrary data in it. And we'll set up our iterator called it. We'll set it to the beginning of the vector. And we'll keep looping until, as long as it is less than the end. The end is defined as being one past the last element. So as long as this is less than the last element, this loop will continue going. And here's it plus plus. And then inside this loop, we will process the dereference pointer to the iterator, which points into the vector. So you'll have a vector element, and you do some processing with that element. So one of the things you can do, because of the nature of the vector, you can say, well, here's an iterator. We'll set it to beginning, and we'll add 3 to it. So it will be, so if this is your vector, let's see, 1, 2, 3. This is where v3i is pointing. This is v3. And they can do that because of contiguous memory and from the fact that it is just like a pointer. So when we print out v3 of 3, and we put space here, and then dereference this iterator, you'll get the same value because you're pointing to the same spot. With a list iterator, you can't do that because of the fact your next could be here. This guy's next is there. It can be scattered all over the place in memory, which is one of the strengths, is what gives you the easy insertion. You don't have to actually move the physical element around. So here we have a list called L3. It's an integer list. We'll load in some arbitrary data, and then we'll loop through it. And because you don't have that less than or greater than, you can't do, where is it now? Here, you can't do this less than. You have to say not equals to. So when it becomes equal to n, that means it's gone one past the n, so it won't go into the loop. So we're going from the beginning until the ending. And this is pretty much the way you have to do it. The reason why I dislike that is because I've seen any number of bugs crop up where someone has gone in there messing with the iterator, they're messing with your loop index, and you go 2 or 3 past the end, and the not equal will not catch that, whereas the less than will catch that because you're now greater than end, so you can exit out of the loop. You should not get that type of problem if you're coded properly, because you shouldn't be messing with your loop iterator inside the loop. People do. You shouldn't, but people do, and the less than will prevent you from having an infinite loop that just keeps going on forever until the system crashes. But this is the only way you can do that with a linked list. Now here's an iterator just like the vector iterator, where we attempt to add 3, and you will get a compilation error. You cannot add integers to iterators for a linked list. Now I have some quick modification. The way you construct a linked list, T stands for type. So we've seen an integer list already. You can have double, you can define a class, and you have a linked list of those class, and then the variable. So here's an empty list. Here you want to construct one with some number of nodes at the beginning with some initial value. You can copy some other list into this list, or you can copy the first and last. These are iterators. This will be an iterator from some other container, and you want to copy from the first iterator to the last iterator from that container into this brand new linked list that you're creating. Now we have a difference between assign and insert. Assign replaces the list content. It throws away the old content, calls the destructor, and replaces it with your new list content. Insert takes the new content and inserts it into the list at some given position. So here we have assign. We take some other list, we grab the first and last and replace it into this list. Or this is pretty much the same as our constructor up here, only we've already built the list and now we want to replace it with new content, and that new content is some number of values. And here's inserting. You have position as an iterator. So you've iterated through the list, you're looking for something, you find it, now you've got to insert something in front of it. So there's your value. Or you've gotten to the position, now you want to insert some number of values, or you want to insert copying from some other list using the iterators pointing to that other container. We can push a value to the front. We can push a value to the back. We can destroy pop front. And not only, pop does not look at it and then destroy it. Pop grabs it and destroys it. So if you need to look at it, call front first. Same thing with back. Erase goes to an iterator defined by this position and deletes that element. And what it will do is it will take the pointers that used to point to that element that you're destroying and point them to each other. Let's give an example here. Just draw a real quick linked list. And it is implemented as a doubly linked list, by the way. So there's a next that points, and there is a previous that points to the previous one, which makes it easy to go in either direction. Now we want to erase this position. Let's say it's pointing to there. We want to erase it. So, okay, let's erase it. And then in the process of doing so, it fixes the pointers to point around where that element used to be. Same thing with a iterator. We've got an iterator pointing to this position, and the last is pointing to another position, and we want to erase it. It will erase them, and the pointers will point around them. So this is the power of the linked list. You don't have to move nodes around. You just move the pointers around. And of course, clear erases the entire thing. So for pop, erase, and clear, each destroyed element has a class destructor. If there's a class destructor, obviously for integers and doubles, you don't have to worry about that. But when you build a class, you have a constructor and a destructor. When you erase the element, the destructor is called, so you can free up memory that's used, that sort of thing. Now we have some more complex modification. You need to merge and splice. There's no construction or destruction done when you're merging and splicing. What you're doing is moving an element from this list into the other list. But again, the actual physical memory stays exactly where it is. So let's say we have this list, and we've got this other list. All we're doing is changing the pointers, and we should use red for that. The pointers point to there, and point to there. So the nodes remain in memory, but having changed the pointers around, it is now moved into the new list. So we can merge from the other list. Merge means that the lists are in order, so we can very easily figure out where to put them. So it will just put them in, and it will remain in order. We go to the other list, and you can have some function that defines. It has to be in order based on something. Is it in order because it's less than something else? Is it in order because it's bigger than something else? But the less function basically returns true if this node should be before this other node. So it will use that function to determine what order to rearrange your linked list. So it moves an entire list into the new list. So the other list becomes empty because all of them have been moved into this new list. Now splice says they don't have to be in order, but this is where I want to put the new list. So if I have a list, and I have an iterator right here, and I want to move the other list in front of this. Yeah, let's say we have this list. So how are we going to work this? This will now point to that, and this will now point to that, and this link is now gone. Or you can move just one element. The iterator points to the one element that you want to move, or you want to range, take from this iterator to this iterator and move them into this list. So it's like the merge, but it doesn't require them to be in order. So you tell it where to go. The splice can move one element at a time. They are removed from the other list, but again, there's no destructors called because it doesn't destroy it and then rebuild it. It just moves the pointers around. So when we reorder things, the list pointers are rearranged. The elements physically remain in memory wherever this. You only have to think about where they are in memory. Just the pointers are moved around. So reverse, we'll go through and reverse the list order. Sort rearranges into some order because we want it to be. We're going to merge these two lists. They have to be in order first. So let's sort them into that order. We have our function, call some function that will do to tell the system what order you want it to be in. In removing, a destructor is called. It destroys the element, returns the memory. So here's where we want to remove everything in the every element in the list that has this value will be removed. It will be destroyed. Here's remove if. We provide a function. It will call this function, says, here's the element, do I destroy this? Your function will look at the element. If it satisfies whatever your criteria is, it says, yes, I want this element destroyed. The element will be destroyed. Unique will go through and destroy elements that are duplicated. Now, how does it know which ones are duplicated? Well, if this is equal to that, then we destroy one of them. The function, you give it the function, this is the function that you should call to determine if these two elements are equal to each other. So here's some quick examples. So here we have a list, a string list called mylist. And we want to add some elements to the list. So this is how it looked at first. My list was Frederick, William, Zachary, Bartholomew, like in the previous slide. So we want to push to the back a new list element called Bubba. So now my list is Frederick, William, Zachary, Bartholomew, and now Bubba. And Bubba is now the end of the list. We want to remove William. So here's the William. Those links are destroyed, and links are created around it so that it looks like this. So these are just some quick examples. Now, you know, this is actually dotted because it actually will destroy. I mean, it's not a matter of grabbing it and giving it to you so you can do something with it. No, it will actually destroy. It will call the destructor. The memory will be returned to the system. So if you need that, you need to actually copy it out, do something else with it before destroying it. Or just don't destroy it. Call move it from that list into another list, and then work with it in the other list. Now, this is something we haven't talked about before. It's actually using a function as a parameter to a function. So you could provide a custom function for these methods. So for example, we have a function for remove if. This is called starts with B. This is something I came up with. We want to remove everything where the string starts with a capital B. So what we're returning is true if the first character is equal to capital B. So I call my list remove if, and I give it that function. So it will apply that function to each node in the list, and if it returns true, removes it. So in our list, Bubba and Bartholomew will be removed. And by remove, I do mean destroy. Now we have functions in sort, for merge and sort. And this example, we want to sort it by putting all the even numbers in order before all the odd numbers. So here's an example. We have even first. We have constant, which means we're guaranteeing to the compiler that we cannot change this parameter. And there's a reference to the first, constant int, a reference to the second. So this is what we're using a integer list here. So our function is, okay, this is taking the remainder by 2. If that remainder is 0, that means it's even. So if the first one's even and the second one's odd, we return true, because all the evens go before all the odds. If the first one is odd and the second one is even, then we return false. It goes that way. And if they're both even, if they're both odd, then neither of these ifs will turn true. So just return the first one is less than the second one. So 2 is less than 4, we return true. 6, or let's say 7 is less than 3, we return false. Not a problem. So we're calling sort, and we're passing in the even first function. So your integer list will be reordered. You have all the even numbers in order, followed by all the odd numbers. Yeah, I know it's kind of a crazy function, but it's quick and dirty, and it's something you can try, and the results are very obvious whether it worked or not. So, having covered most of the list with a few adapters that use linked list. The first one is a deck. It's kind of a combination vector and list. It has fast insertion removal from the ends, because it can allocate space and grow in either direction. Insertion or removal in the middle might be more efficient than with vectors, but less efficient than a linked list. Basically, internally, what it will do is break. If you had a contiguous piece of memory, like an array, and you need to insert something in the middle, it will work something where it splits that into 2 pieces and do a linked list type of thing for your insertion. So it's not as bad as having to move all the data in a vector, but it's not as quick as a linked list. So it's kind of in between here. So insertion at either end preserves existing iterators, which I found peculiar. Now, it's not guaranteed to be contiguous memory, because as you see, we just added something, and the memory is now semi-linked list. But it allows you to use the array operator or the at method to access it as if it was contiguous memory. So you have pretty much the same methods as a vector, but you also have something where you can push a value to the front or pop the value from the front and destroy it. Our next one is a stack. Now, you may or may not be familiar with a stack depending on how much computer science experience you've had before. Basically, what a stack is, you think of a stack of plates. That's the classic example. You have a new plate, you put it on top of the stack, and it pushes all of them down. You get another plate, you put it on top, and push them down. You get another plate, put it on there. When someone comes in, these are all your clean plates. You have a clean plate, and you put it on the stack and push it down. When a customer comes in, I need a plate to go get some food, you take a plate that's on the top, and you go get some food. You take the plate that's off the top, and you go get some food. Now, why do we do things like that? In computer science, you have a number of examples, particularly like in compilers. When you call a function, it will take the environment of your system that's there, and it will put it on the stack. And then it will switch over to the function, and you have all new variables. It will take a new plate, which is all the memory that the function requires, all its variables, everything else in there, and the function will use it. If the function calls another function, it gets another plate. Let's say we got F1. I'm not sure whether you see that or not. And the new plate with the new function with all of its variables gets placed on the stack. Now, when the internal function ends, it has to return back to the function that called it. So that plate is taken off of the stack. So now you're back to the one that was underneath that, which is this function. When that function ends, that plate gets taken off, then you're back to your main routine again. So that's pretty much what a stack does. Again, is the stack empty? How big is it? Give me a reference to the element on the top. Take a value and push it on the top, or take the value that's on the top and pop it, which destroys it. You may want to call top before you call pop, because if you call top after you call pop, you get the one that was underneath the one that was just destroyed. If you want to look at the plate that's on the top, use call top first. And if you want to get rid of that for whatever reason, then you call pop and it gets destroyed. And that's all we have. There's no iterators, no inserting into the middle. The elements of the stack are only accessible from the top. That's how a stack works. Then we have a queue. Now, you may have actually seen queues in real life. Basically, it's like you're waiting in line. You have a line of items. You're over at Taco Bell or whatever you're at, and the first guy gets his tacos, and then the next guy gets his tacos. You come into the store and says, I need some tacos. Go to the end of the line. That's how a queue works. And again, it's an adapter. It will use some other container to do all the heavy lifting, probably a linked list. Is it empty? How many elements? It gives you access to the front of the line. It gives you access to the back of the line, which is not really a pure queue. A pure queue, all you can do is push things to the back. You can't actually look at the thing that's on the back. And then when you push the value, it gets placed to the back. Go to the end of the line. A new customer comes in. Go to the end of the line. Pop destroys the first element at the front of the line. So you look at the front, and you service that customer, and then you destroy it from the queue. So things keep moving in the line. And again, that's all. There's no iterators. You can't insert into the middle. They're only accessible from either end. You can put them in that end, and you take them off the other end. And actually, I like this kind of list. I have a long list of things I want from Santa Claus. And so that's it for today's lesson on Intermediate C++. We've talked about lists and decks and queues and stacks, and we'll see you next time.